Hello, my name is Aashik Nagadikeri Harish, and this is my presentation on the wireless communication project for the spring semester. The topic of my wireless communication project is analysis and comparison of various error detection and correction codes. These are the list of topics that will be discussed in this presentation. Now, let's move on to the motivation slide. The main reason for doing this project is to gain insight as to why different error detection and correction codes perform differently for different applications. This helps us to gain intuition to use the right error correction code for a particular application. Let's move on to the introduction slide. As you know, wireless channels are subjected to a lot of noise, which leads to corruption of the data bits in the transmitted message. Using error detection and error correction schemes, we can detect and rectify these errors. These are the various error detection schemes which are analyzed in this project. Let us look at them in detail. The first error detection scheme that we are going to look at is checksum. In this scheme, a checksum function is applied on the data to calculate the checksum, which is then appended to the data when transmitted over the channel. At the receiver end, the data and checksum are separated, and the checksum polynomial function is once again applied on the data part to see if the calculated checksum matches the one sent by the transmitter. If they are different, it indicates an error has occurred during transmission. Now, let us look at cyclic redundancy check. Here, a known generator polynomial function on both the transmitter and receiver side can perform long division on the input data and calculate the remainder which is sent along with the data. The same generator polynomial function is then applied at the receiver end to perform long division. A zero remainder in this case indicates that no error has occurred, while a non-zero remainder indicates an error has occurred during transmission. Let us move on to cryptographic hash functions. Here, a special math algorithm is used to map data of arbitrary size to a string of fixed length called a key. Using this technique, the hash map can be quickly calculated and is unique for each and every data. The advantage of this technique is that the probability of collision occurring is quite low. Let us move on to parity bits. This is a very simple technique, and there are of two types, odd and even parity. Even parity adds 0 to the data if the count of the number of bits is even, and 1 if the count is odd. Odd parity, on the other hand, adds 0 or 1 if the count is odd or even, respectively. The table contains a few examples of odd and even parity for different sized inputs. Here, as an example, you can see we have 101 and the number of bits is 2, and hence the odd parity is 1 while the even parity is 0. And the odd parity is appended here while the even parity is appended to the message here. Let's look at repetition code. It is the simplest and least effective technique used in error detection. Here, the bits are repeated and sent multiple times to the receiver. At the receiver end, a majority vote is performed to see if any of the bits have changed. It cannot detect errors when the bits in a particular location have changed for all the blocks. Let us move on to error correction now. These are the various error correction codes that have been analyzed and discussed in this project. First, let us take a look at Reed-Solomon code. Redundant data or parity bits are added to the data before transmission. An addition of 2 T parity bits can enable detection of errors up to 2 T bits and correction of errors up to T bits. They are widely used in storage devices like CD, DVDs, Blu-ray, and also in space communication. Let us look at LDPC codes or low density parity check code. These codes can be constructed using vertices of graph that can be divided into 2 disjoint sets as seen in the figure. An iterative algorithm is employed here where the message is sent to and fro between the message and check nodes. They are highly reliable and have very fast encoding and decoding process. Let us move on to BCH codes. It is of a relatively simple design where the user is given freedom to choose the number of bits that can be corrected in the system. It uses syndrome decoding for decoding multiple bit errors and are widely used in storage devices. Let us move on to turbo codes. These codes were the first of its kind to approach the channel capacity as proposed by Shannon. The use of interleavers in this case leads to a very slow encoding and decoding process, but they are very good in addressing burst errors by shuffling the source symbols to give an uniform distribution of errors. It is also used in space communication. Let us now look at the Hamming code slide. This code makes use of extra parity bits to detect an error. The diagram in this slide represents a 7,4 Hamming code where there are 4 bits, that is 4 data bits represented by the letter D and 3 parity bits represented by the letter P. The parity here is calculated for a certain number of bits in the code. It can detect and correct single bit errors, and it finds its application in dynamic RAM. Now let us look at convolution codes. These codes, unlike the various block codes that we had discussed in the previous slides, can work on symbols of any given length. It makes use of a dynamic programming algorithm called Viterbi algorithm for decoding purposes, and it's used in wireless cellular communications. Now let us move on to the results of my project. Let us look at the results of the various error correction codes implemented here. I have calculated the efficiency by plotting the bit error rate against the various values of SNR. The tabular column in this case shows the error statistics for a few values of SNR. Here in Reed-Solomon code, you can see the drop in BER with better SNR follows a sort of a polynomial curve function. Let us look at the results for the LDPC code. Here, as you can see, the bit error rate is quite low. It ranges from some 0.32% to 0.06%, which is really good. Here, the bit error rate has a sudden drop after it crosses the threshold of 0.7 dB. Let us move on to BCH code. For BCH code, the BER SNR curve follows a similar kind of a polynomial function as we saw in Reed-Solomon code, and it also has a very good bit error rate, ranging from around 3% to as low as 0.35%. Let us now look at turbo codes. For turbo codes, I have plotted the BER against the EB by N0 values, which is nothing but the normalized SNR or the SNR per bit. Here, I have plotted them for both the encoded and the unencoded signal. The orange line indicates BER for the unencoded signal, and the blue line indicates the BER for the coded signal, and we can clearly see the better performance of the bit error rate for the coded signal. Let us look at the results of Hamming code. Blue line indicates hard decoding, where decoding is done using Hamming distance, while the orange line indicates soft decoding, where decoding is done using the Euclidean distance. As you can see, soft decoding gives a better bit error rate performance. Let us look at the last result slide. In this graph, we can see that the bit error rate hovers around between 0.49 to 0.51, that is around 49 to 51%, and it does not improve significantly for different values of SNR, and you could say it almost remains the same. Now, let us look at the conclusions derived from this project. Here we can conclude that a single error correction scheme cannot give us the most optimum performance for different kinds of applications, and they are usually dependent on a lot of characteristics like latency, noise in the channel, hardware type, design type, and error type. These are the major references that were used in this project. Now, let us move on to the demonstration of this project. The demonstration is present in the next video.